Welcome everyone to geohug. So I'm very excited. We've got Gavin Clarkson with us today. So it's going to be a really great session. So I hope you all have a lot of fun. I'm just promoting you up as panelists now, so don't be shy. Come on through, get the cameras on, get the mics on, and we'll be opening up for some great discussion at the end as well. But yes, before we do kick off today's session, I would like to take this time to acknowledge the traditional lands which we're all coming from today. I live on the beautiful lands of the Gadigal of the people of the Aurora Nation. I'd like to pay my respects to the elders past, present, and future. And yes, I'm very excited that we have Gavin Clarkson with us today. So Gavin is the Business Development Manager of Hexagon Mining. He's over 15 years of experience in the mining industry, starting in grassroots exploration before moving into technology and software solutions. And it is going to be brilliant hearing from him today as he gives us an introduction to the foundational model of mineral estimation. So we'll be getting an overview of what variograms are and see some awesome visualizations as well. So it's going to be a really good session. So thanks everyone for joining. And yes, thank you so much, Gavin, for being here. It's awesome having you.
Yeah, thanks very much for having me.
Before we get stuck in, I was curious what got you into geology and mining in the first place.
So I'm in Vancouver now. That's where I'm based, but I was born and raised in Whitehorse, Yukon, which is northern Canada, and it's a very mining-driven part of the country. And my dad's actually a mining engineer who specializes in placer gold. So I spent much of my pretty much as soon as I could carry a bucket of dirt, I was being employed in some capacity doing sampling or drilling or some sort of gold campaigns with my dad in the field. So that's kind of where the idea behind becoming a geologist engineer, being involved in the mining industry was really planted.
Wow, that's awesome. Where have been some favorite place, like growing up in the Yukon? I imagine you're very lucky for outside adventures, but yeah, what have been some major highlights for you?
Yeah, so for career-wise, I think some of my fondest memories were probably back in grassroots exploration with tech, even just doing simple soil sampling campaigns, because it isn't very often that you get to go to work in a helicopter, which is the fun part about geology. I do look fondly on those days. I did go into technology though, because I did want my summers back. It's really fun being in grassroots exploration when you're, a teenager and in your 20s, but eventually you want to know what your own home looks like. So
Yeah.
I swapped over to technology shortly after my master's.
Oh, that's awesome. And through your adventures, I ask everyone to bring some of their favorite pet rocks along. I was wondering which treasures you've brought along with you today.
I got a couple of examples. This first one, this is a fire opal that a friend of mine named Matt Krakowski, he was one of my, it's a little blurry on the Zoom there, but it's got really good color to it.
Beautiful.
Thank you. One of my undergrad compatriots, Matt Krakowski, his family has a opal claim outside of Tucson in Arizona, and he's also from a family of jewelers, so they cut and polish them themselves and make gorgeous jewelry out of them. And he gifted me this in my first year with Hexagon when I was down at their headquarters in Tucson training, and he came and visited me and gave me that. So that's super neat.
Nice.
And then my other bit, this is a little not quite a pet rock, but it's a neat example. My first year as a geology student was with the Yukon Geological Survey, and I worked with Bill Labarge, who is a geologist that specialized in placer gold, and he would always do annual visits of all the placer mines and do updates for his annual report. And each year he would make one of these, which is a placer gold scale, and that's real gold, the real gold flakes in epoxy. And that was my first task with the YGS, was making a bunch of these. He only made 10 or so a year because it is real gold in it. And it's a quick visual scale. So when you're panning, you have a rough comparison estimate. So you can say, oh, it's about 2 milligrams of fine gold or coarse gold or something like that.
It's a reference card for alluvial gold. That's brilliant.
That's really
It's super neat.
Cool.
Yeah. And he would print a bunch to give away, but there was a select few that were real and actually had real gold flakes and epoxy, and I got to keep one of them because I was making them for him. So he made about a dozen each year to give out to his favorite people.
And
I botched the epoxy in one of them.
Then too, right? The price of gold was not so high back then.
It wasn't as much. No, this card might have been worth a bit more now than it was then, for sure. I think it was probably 1,100 an ounce, I think, when I was working in that capacity, somewhere around that.
Okay.
But,
Wow.
It's a little different now.
You're young. You're young. You're gonna age people on the price of gold that they remember.
I know, right?
Nice.
I love this. Oh, well, thank you so much for sharing that with us. And thank you for joining. I'm very excited to hear your presentation today. So yeah, if you want to share your screen and we'll get into it.
Excellent. Okay. So when I was invited to do this session, so I'm business development manager here at Hexagon, but that's only in the last year or so. Before that, I was one of the geologists and mine planning specialists here, and I specialize in our MinePlan 3D software, which is our engineering and geomodeling software. So it does everything from drill hole management to geomodeling, geostatistics, interpolation. Then once the model's all finished, an engineer can grab it in the same software, do all their long-term plans, pit design, scheduling, and so forth. So I coming from a geology background, I specialized in the geoscience part of it. And during my time in Hexagon, I did some education in geostatistics and was able to get more and more specialized in sort of the interpolation realm of the software, which is still something I'm very interested in. So when I was asked to do a talk for a bunch of other geologists, I figured a word that comes up a lot in a geologist's career and a word that you don't necessarily know or understand, because it certainly wasn't taught when I did undergrad and even in my master's. It's something that you really had to seek out the information from. So I wanted to do just a primer for what actually is a variogram. What's its use? What does the shape mean when it shows it, and how those little curves and dots are actually calculated. So these are extremely basic examples with some fudge data that I've made up to be very visually instructive, and breaking it down to also be really, really basic with just some one-dimensional examples. This is meant to be very math light. We're not going into the math of what kriging is or anything like that, just at a really high level. What is a variogram practically telling you, and what is its practical use? And all the examples I'm using are any of the 3D ones you see are going to be using MinePlan, and a couple of examples I've pulled from other places, and I've sourced them appropriately where that's the case. So starting off, just because not every geologist is in mining, so just a real quick 3 slides on what interpolation is and why we're doing it. And then second point on just really basic what interpolation is, and it's just essentially a weighted average. How you weight that average is where it gets fun. And why we do that. So deposits are very often spatially distributed. So there's going to be differences depending on what distance and direction that you're comparing between. And then back to basic math, because if anyone was like me, they went to geology because they enjoyed pencil crayons a lot more than they enjoyed doing math. So I wanted to make sure for the geology group that I did a real quick review of variance and basic statistics on just with a simple example of dog heights, just to kind of prime your minds on what an average difference means. So that'll help us leap into what a variogram actually is. And then variograms, I'm going to go through a really basic one-dimensional example of what you're doing when you do a variogram, what lags are, as well as experimental variograms after. So variograms are going to do a quick one-dimensional example, and then what an experimental variogram is versus a variogram model, and what the difference is and why you do either. And then a quick overview on how variograms are built practically, because the one-dimensional example I'm going to do is very idealized, and not when you actually get into real data and in 3D space, it gets a little bit more limiting. So we're going to look at how you actually build those variograms and the different limitations on lag tolerances, things like that. Then we're going to look at a few 3D examples in MinePlan of what variogram modeling looks like with more practical data. And this is what the data set that I've invented with a super, super strong high grade trend. You'll see it. It's going to have a drill hole density and grades that you wish you'd see in the real life, but never will. But I like using it because it's very visually striking on what a variogram map looks like. And then we'll just summarize what we put together there. Oh, and I also have a little asterisk there for any sticklers in the group. I'm going to be using the terms semi-variogram and variogram interchangeably. I know I shouldn't be doing that. This is real basic example, so don't call me out on it. I've already covered it here. I know they're different and I know why, but just for simplicity in the industry and in much of the literature, they are used interchangeably. And we can go over that in the discussion as well on what the difference there is, because that was surprisingly hard to find in my research. Alrighty. So mining 101, why do we interpolate? What are we doing when we say we're interpolating, and where does that all come from? So this is just my 3-slide undergraduate degree on what mining is. So you have drill holes, which we see on the left. These are your known sample points. These are logged in the field, written down by geologists, and then parts of it sent to a lab so you can get the geochemistry from it. So you know exactly how much metal is in a certain length of your drill hole. Then you put it in a colorful visualizer like this. And then through either an implicit model to do the job for you, or through digital cross sections, and more commonly through a combination of both, you create your geological boundaries, since grade is often restricted by some sort of boundary. So you go from your geological logs, so your known data points, your drill holes, your samples, and you make a geological model from it. And then from that model, you do a bunch of fancy statistics and interpolate the grades into a block model, using those geological boundaries as kind of domain boundaries, depending on what type of deposit you have. And a block model is just a set 3D volume that has been assigned a grade or a geological code or any other sort of calculation that you then use in your mining plans. Typically, the mining unit about the size of what a single bucket of whatever your equipment is. So how that's chosen, again, is a whole fun journey in itself. And then that block model is given to your engineers, and they do a bunch of fun math on it and figure out what your pit design or your underground design should look like in order to extract it into a series of plans. And then that pit design is broken up into a bunch of individual cuts based off of different grade or value criteria. And those cuts are assigned to different profitable destinations using a series of schedule optimizers and calculators to make your mine economical. So that's Mining 101. You can collect your degrees at the door. And what we're concerned with is the interpolation aspect of it. So an interpolation is your best guess or your best estimate of an unknown point in your mine, because every point in your 3D block model you need populated to do your plans around, but your samples aren't that closely based. So you need to guess in between your known points or samples what's actually happening within those blocks. So that's what an interpolation is. And for every interpolation, every individual block is looked at. And from the center of that block, it selects a series of the known samples around it from a variety of distances and from a variety of locations, and then does essentially a weighted average, a best weighted average. Those samples are weighted depending on where they are relative to the block, where they are relative to each other, and depending on how they're compared with your variogram model or your search distances, it is given more or less influence on your final estimate. But any interpolation is essentially just a weighted average, and calculating the weights for that for any individual sample is where the variograms come into that. And then the geological boundaries that you created earlier control what samples are allowed to be selected for an estimate. And you also typically do a search ellipse around each block to ensure that you're not looking, kilometers away for any individual samples and those limitations. Okay, so let's do some simple one-dimensional examples. I did say this was going to be math light. It's unfortunately not going to be math free, but it will be math light. So we're going to start just by going over a basic interpolation. In this case, we're going to do an inverse distance interpolation. And using this really simple example, we have the little block there on the left, and we have two samples, one with a grade of 0.5 of gold or candy or whatever it is you happen to be mining, and then 1.1 over here. And in this example, the two samples that we're using to guess or to estimate the value, the best estimate of this value of this block, is it going to use these two samples that are equidistant apart. They're both 100 meters apart. And an inverse distance interpolation is just saying, make this block an average of the surrounding closest grades, but closer samples get more influence. And in this example, the samples are equally distanced, and with inverse distance, that means they get weighted evenly. And here's the equation here. I didn't print it out, but you can kind of break it down. You can see 1 over the distance squared. This is why it's called inverse distance squared. That's this exponent. You'll also maybe hear in the industry inverse distance cubed. You can essentially put any exponent in there you want. The higher the exponent, and the more quickly a sample is punished for being further away. So it's going to be less influenced. So in this example, we have 1 over the distance of the sample squared times the sample's value plus 1 over the distance of the sample squared, so in this case, they're both 100, times the sample's value, divided by the sum of the inverse distance. And in this case, the estimate becomes 0.8, which ends up just being average because they're weighted the same. So each of these grades gets an equal weight, so the grade assigned to the block becomes pretty much just the straight average, 0.5 plus 1.1 divided by 2. And that's basic inverse distance result. And all it's concerned about is distance from the block. It doesn't care where the samples are. And as a follow-up example to that, here's a similar scenario with the same grade values, but one of them is slightly further away. With uneven distance samples, the closer sample gets a greater influence. It's weighed more, so it gets a greater weight on that weighted average. And the further sample gets weighted less. So despite the grade values being the same, the lower value, the 0.5, gets more influence over the overall result. And you can see the calculated weights down here. The 0.5 got a total weight of 0.8, and the grade of 1.1 got a total weight of 0.2. And all your weights will always add up to 1. That's how a weighted average works. So the majority of the weights, 80% of it, went to the closer sample. So despite the two grades being the same value, you got an estimate of 0.8 when they were equally weighted, and an estimate of 0.62 when the lower one was closer, because it is more weighted to that sample. So again, inverse distance, only concerned of how far away the points are, but not where the points are. Only distance is considered in an inverse distance interpolation. You can change the placement of the samples and without changing the distance. So if I take that same example and rotate it a little bit and change where the samples are, the result is going to be exactly the same as at our first example. It's going to be 0.8. It doesn't care where the samples are. It only cares how far away they are from the block. So you can change the placement and not the distance, and you'll get no different result. And this is an important consideration in geology. Deposits are often, if not always, structurally or geologically controlled by some boundary. There's some sort of orientation or some sort of direction that your ore has been deposited, or that your metal of merit has been deposited. So that orientation, or where those samples land, can become very important. And that's where variograms come in. They can take this weighting into account, but also consider where your samples have landed. So consider if we could weight the samples not only by how far away from they are from the block, like the simple inverse distance result, but also where they are. So this is essentially what a variogram model does. It's going to estimate how different an estimate, it's going to tell you how different an estimate should be from a sample based on that sample's distance and direction, not just how far away it is, but also where it is relative to the block. So by weighting distance and direction, we can model these estimates more spatially. We can actually consider where they're landing and weight them based on that. So deposits usually have some sort of a spatial relation. There was something that happened that caused that metal valley to drop out or to concentrate in the area that you're mining. So they're spatially restricted. The mineralization occurs along sources or pathways. There's some sort of favorable geological condition that caused those metals to drop out of solution. And this imparts a spatial correlation. And this one, for example, here, if we're imagining that these are high value ore veins, you can imagine that two samples separated a large distance or across the vein might be more similar, or sorry, at a large distance along the vein might be more similar to each other than two samples that are taken at a short distance across the vein. So where the samples are coming from and how they become weighted becomes very important. Alrighty, so let's do a quick little pause on geology, mining, all that good stuff. We're going to go back to some basic statistics because we're going to talk a lot about like the average distance, or essentially the variance. So variograms aren't exactly variance, but they're pretty close. So I like using kind of a step backwards to check out what variance is and how it's calculated. So the variance, when you hear that, is a statistics term that you would have heard potentially in high school math, definitely in your undergrad. It's all like the mean, variance, standard deviation, all that basic statistics stuff. So the variance is just the average squared difference from the mean. And it's this equation here. But I said this would be math light, so we're going to replace the math with fun dogs, because dogs are better. And we're going to use this dog height chart as an example of what variance is. So we've got our data series, which is 5 dogs, and we've measured the weight of these 5 dogs. We have 5 data points, and we have 5 dog heights. And we've measured them each of their shoulders, and those are the values there. So to get the average squared difference from the mean, we need to get the average squared difference we need to get the average first. And the average is just, you probably remember, the sum of all the values divided by the number of values. So the sum of all of their shoulder heights divided by the number of dogs, and this is your mean. And then to get the average squared difference from the mean, we have our mean now, so we can just find what the difference from the mean is. So this guy's taller, so he's 206. This guy's 76. This guy's shorter, so he's negative 224, which is also why we do the square difference for the mean to account for negatives and also account for values canceling each other out. There are other ways of doing summary statistics that don't necessarily use the square, but we won't get into those. So in 36, near the mean, negative 94. So the variance is just the average squared difference. So it's just these differences squared, and then the average of that number. That's the variance. That's all it is. So when I mention average square difference and we start looking at the variograms, it does a very similar equation, except on a comparative data set. And I'll get into what that means shortly. But for now, average square difference for the mean. We have a value, we have the difference from it, we square those in order to cancel out any negatives and to balance it better, and then we get the variance. And then in most cases, you'll take the square root of that to bring it back to the original units of your measurement. It's because 21,704 doesn't tell me much about how tall dogs are. That's a pretty monstrous dog. So we take the square root of it to get the standard deviation, and we get 147. So we have the mean. We know what the average height of all the dogs are, 394, but we don't know if that's all dogs that are exactly 394 millimeters high, or if it's one really short dog, one really tall dog, that kind of thing. So that's what the variance says. It gives you a range of, on average, this is how different everything in this data set is from the mean. That's what where we get that average square difference from. And the standard deviation, take it back to original units, is the square root of that. Alrighty. So now that we've kind of got primed around the math of what an average square difference is and all that terminology, with an example of dogs, let's go back to some samples. Let's say the line at the bottom is all a series of drill holes with some sort of grade assigned to them. And they're separated by exactly 100 meters because that makes it super easy. So a variogram is measuring from here to there. What's the average square difference from here to there in that direction at that spacing? So let's say I have a line of sample points oriented left to right. So the direction we're looking is left to right. And let's say I've got an unknown point, that block on the far right there. And it's along the same direction, so from left to right, and it's 100 meters away. And I want to know, like, how should I weight samples nearby it? Like, how different should it be from its surrounding samples in that direction? So for all my known points, so I have all my known sample points here, and I want to know that for that 100-meter spacing that I want to know if estimate an unknown point for, on average, how different should it be based off of all of these other sample points? So I'm going to look at all these other sample points and compare them to each other, any point that's 100 meters away from another point, and compare what the average difference is between those along a certain direction. In our case, the direction is left to right. So the distance we're using, we're going to use a fixed distance of 100 because that's the distance I'm interested in between all points in this data set, and figure out what the average difference between any of those points are. So difference, distance, and direction. And you start collecting a comparative data set like this. So going from left to right, we start collecting a sample set of tails and heads at that lag spacing. So I keep saying distance at 100 meters. That's what our lag is going to be. And that's another term you'll hear a lot in variograms or in interpolation. So right now we're using a 100-meter lag, and we're collecting a series of tail and head points and getting the squared difference between them. So in this case, I've got my 100-meter lag, and I'm going to look at this one to this one. So that's my tail value is 0.8. My head value is 0.65. And I'm going to move down the row. Now my tail value is 0.65 and my head value is 0.85. And I'm going to move down the row. My tail value is 0.85. My head value is 0.75. And I'm going to do that for every point set in this direction at this distance. So every sample that's separated by 100 meters. Until I get a table that looks like this. And don't let the summation function scare you like it scares me. It isn't as complicated as it looks. This is what the equation is for a variogram. And all it's saying is, or semivariance, technically, that's what that number 2 is. So don't call me on it. So what's the average square difference from here to there in that direction? Remember, we got the average square difference for those dogs from the average for their shoulder height. Now we're getting the average square difference of our tails and our heads. So what the equation is saying is that my variogram value is the sum of the difference between my head and my tail, that's this I and the J, squared, and then divided by the number of data points. So that average squared difference, much like with the dogs. So we're taking all these values, that 0.8, 0.65, 0.65, 0.85, 0.85, blah, 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 blah. The only difference here is we're not doing the difference from the mean, we're doing the difference from each other. So the difference from this tail to the head. So the dogs, we're doing the mean, these ones, we're doing a difference from each other. So this is written out, this is written out in the equation, but most simply, it's just this. The square difference of the tails and the head, summarized to get that 0.32, divided by the number of pairs, n, which is 10, and then double that because the number of pairs is now the number of discrete data points. That's why it's this number 2 is why it's called the semi-variogram, because I want to actually know what the average difference is for each individual point, not the pairs. So now we have this value. And what that value means is where we're going to be on the variogram. And that's what I'm going to get to next. So we now have a value for a certain lag spacing. So for every sample, for any sample anywhere in my deposit, when 2 points are 100 meters apart, on average, they're going to be this different from each other. And just to compare it back to the dog examples, when we were calculating the variance, we were getting the average squared difference from the mean, which was their average shoulder height. The only difference we're doing here is we have a scatter plot. We have 2 different data sets. We have tail values and we have head values, which were just the tail of the arrow and the head of the arrow for our lag. And we have a scatter plot of head and tail values, and they have a line of equivalence here. So this x equals y, this is where a grade is, where a grade of a tail value is equal to its head value. So when 2 values separated by 100 meters are exactly the same, they sit exactly on this line. And the variogram is looking at what is the average difference of those values from each other. So on average, how different are all these lines on this, or all these points on the scatter plot from their equivalency line? And also gives you an idea kind of on the correlation of it. And I'm going to show you a comparison of that as well. So instead of doing the difference from the dog shoulders, we're doing the difference from equivalency for this data set, the tails versus the heads at a certain spacing, in this case, 100 meters. Ready. So what if I want to do that calculation for another block, except this one's 200 meters away? Now I need to know for any samples that are 200 meters away, what's their average difference? How different would I expect them to be at 200? You might be ahead of me on this one. We just do another lag spacing, except this time at 200. So lag is the defined spacings used to calculate variograms. You collect tails and heads at certain lag spacings. We started at 100. Now we're going to do 200, and we're going to calculate the next value on our variogram for that spacing. And it's exactly the same, except the arrow is twice as long. We collect the tails and the heads the exact same way, looking in this direction. So we're looking at a certain distance, which is lag, for the average difference between all the points in a certain direction, which is left to right. So now, same thing, our tail is 0.8 at a 200 meter lag. Oh, I got to update that. I'll make sure to update on that side. That should say 200. So going left to right for 200, we're going to collect a tail and head. In this case, it's 0.8 and 0.85. And we're not skipping anything. We're not leapfrogging. We're doing this for every single point. So I'm just moving to the next point, and its tail value is 0.65, and its head value is 0.75. And we're doing the exact same thing. We collect all of these, just like we did with the other lag value, until we have a table of tails and heads. We get the average square difference divided by the number of points, and we have our variogram value. So on and so forth until you have a bunch of lags and a bunch of points. Or sorry, a bunch of lags, variogram values for a bunch of different lags. And those are what become your variogram. So this is what's known as the experimental variogram because it's individual points. I actually collected data pairs to come up with any of those individual point values at each of those lag distances. So at each distance, you calculate the average difference for all samples that are separated by that lag distance. For each lag, you summarize the difference between all points of your data separated by that distance and in that direction, and you get that single data point. And you place that data point, so that variogram value that we calculated, and that's on the y-axis. And on the x-axis is the lag distance you calculated it at. And typically in nature, as values are further and further apart, they're less and less correlated with each other. They're less related. You expect 2 samples you picked up within arm's reach of each other to be more similar to each other than 2 samples that are maybe 300, 400, 500 meters away. You would expect them to be on average more different. And that's what you tend to see in a well-behaved variogram. It climbs to a value beyond which they're no longer related or correlated to each other. So at some distance, or at some lag distance, in this case about 400, so for samples 400 meters apart, and this is beyond my one-dimensional example, this is using some data. So this is saying that samples that are between 0 and 50-ish, very closely related to each other, and then around any samples that are separated by 500 meters are no longer all that related, and that's the SIL. That's the value, the distance, the lag separation at which samples are no longer correlated to each other. And I'll summarize that in a future chart. But just to highlight, every individual point of this variogram represents this set of data that you collected, the tails and the heads. So for any individual variogram point, you actually have a little scatter plot of those individual tail and head values. And this point on that y-axis represents, on average, how different are they from each other. And as variogram value increases, correlation decreases. So correlation is, or the correlation coefficient, this is a measure of how related these two samples are. And for low measures of variance for a variogram, they're quite related to each other. And that just means that typically if the grade of a tail sample is low, the head sample grade will be low as well. And that's a positive correlation. And then in this example, as my lag separation gets bigger, let's say this was at my 100-meter spacing. So if in my deposit, if you're only 100 meters away from the sample, you're going to be pretty similar to it. They're going to be pretty well correlated on average. And you can see that from the scattering of tails and heads that was collected. For any samples that were separated by 100 meters, its tail value was pretty close to its head value, or at least if one increased, so did the other. And as separation increases, that correlation goes down. You can see the correlation coefficient gets smaller and the variogram value gets bigger until you're essentially uncorrelated. The value of your tail grade has nothing to do with the value of your head grade. They're no longer related. One can be low while the other is high. They're not necessarily growing or falling with each other. And that's what I mean when they're uncorrelated. The scatter plot no longer has any sort of discernible trend. They're just kind of randomized. And that's what the SIL is. So when you're looking at a variogram, each of these individual points is actually a collection of head and tail values separated by that certain lag distance. Okay. Alrighty, now that we've discussed a bit over how we make those points, we'll look at just a couple of definitions that you'll see for our variograms. Oh, sorry, that's on the next slide. This is actually about the variogram model. So the experimental variogram, these are individual points that I've actually collected heads and tails for at certain variogram spacings. Let's say at 100, 200, 300, 400, etc. But what if I wanted to estimate an unknown point at some distance that wasn't a lag? What if I had a block that I wanted to guess that was at 226.3 meters and wasn't well behaved at 100 or 200 or 300? And that's why we fit a model to it. So a variogram model is just fitting a curve to those experimental points so that at any distance, because remember the x-axis here is your distance, at any distance I can go up to the y-axis, find my intercept, and then know what the variogram value should be for that distance. So I'm no longer constrained to the calculations I made at each individual lag. So your experimental variogram are the points, and then your variogram model is the curve fit to the points. And once you have that curve, any distance can now be calculated along that direction. Okay, and since I've shared the classic image of a variogram, we'll go over a couple of the attributes and definitions of it. I mentioned briefly the range there, the distance of separation where samples are no longer correlated. So you can see there's an increase as samples become further and further apart from each other with greater and greater lags. Your variogram value tends to increase because they become less and less correlated. At some point, that typically tends to level off, meaning that they're no longer related to each other. There's no greater spacing causing greater correlation or decorrelation. They just kind of tap off. And that's what's called the range. This line here in the sand is essentially saying if samples are this far apart from each other, they're no longer related. They no longer have anything to do with where you're estimating your point. And then the SIL tends to be where the variogram flattens off. People often use the variance of the data set as part of the SIL. You can also model it depending on where your variogram value cuts off here. But values can go above the SIL. They just mean that scatter plot becomes negatively correlated. So in the previous examples I was showing here, this is a positive correlation. So as one sample value goes up, the other one tends to be high. And negative correlation is the opposite slope. So as one increases, the other tends to decrease. So if you have points in your variogram above the sill, that tends to indicate that the scatter plot underneath that's generating that point, like we saw here, is negatively correlated. Okay. And then finally, there's what we call the nugget effect. Ideally, if you took two of the identical samples, they would have no difference from each other. But anybody who's done a core split knows that's often not the case. When you have two different samples that are done at the exact same place with zero distance, so zero distance would be at the y-axis here, they should have zero difference. But not always the case of it. So that's why in practicality, you often have to model a nugget, which is the inherent variability of your deposit or of your ore or whatever it is that you're measuring at zero spacing. So like, and the term nugget comes from the idea that if you did a core split at the exact same place, one has a gold nugget, one does not. So that means that one is very low grade and one is very high grade. So you get an inherent difference in there. Mathematically, not necessarily what it means, but just in practicality, you often have to model to a nugget effect because of those split values. Okay. So those are the basic definitions of the kind of common variogram attributes. And then since we're talking about definitions and practicality and things that you have to do in reality, a couple of other terms that you might come across. There's the lag tolerance, because we were looking at lags that are exactly 100 meters apart. In reality, your samples probably aren't going to be exactly 100 meters apart. So if you are really strict with that distance tolerance, you're going to get very, very few data points that you're collecting for your tail in your head, because you're only going to be looking for samples that are exactly 100.00 meters apart from each other. So in practicality, when you're building a variogram, you use what's called a lag tolerance, where you say, okay, my lag 1 is going to be 100 meters. But if the samples are within 90 to 110, within that range, we'll still count those as lag 1. So it's a bit of an overlap you put in so that you can actually gather data. Same with the azimuth tolerance. It's the same idea, because any variogram, we were looking left to right. Remember, we were looking in a certain direction to collect our data points. So let's say that was an azimuth of 90 degrees, east to west. If you did an azimuth of exactly east to west, same problem, only samples that were exactly on that azimuth from each other. So a sample that was exactly east-west of the ones it was measuring from would be collected as tails and heads. Again, that's really going to limit how many data points you actually get for that variogram. So you use what's called an azimuth tolerance to create a bit of a cone of visibility for it to collect its data points. And finally, there's the bandwidth. If you put an azimuth tolerance, the further you get out, so the bigger your lags get, the bigger your separation distances get, the wider your cone is going to get as well. So typically a bandwidth is put in to restrict that cone to some radius. So eventually you get something that looks kind of like this. So this is one data point, so one composite point in a drill hole, and it's looking in a certain distance, and it's being split into certain lags along certain, so it's looking a certain direction, and these lags are its distances that it's looking in. So you can see this kind of cone of tolerance that's been put around it, because in one dimension, sure, it's great to only look at samples that are 100 meters apart exactly, but you're going to have very few of those, or samples that are exactly on this azimuth that you're looking, but there's also going to be very few of those. So you end up collecting your heads and tails for your different lag distances with a certain sort of cone of tolerance around each. So a bit of a flashlight that you're shining down to be able to see actual sample pairs across that. Alrighty. So we've looked at a little bit of a one-dimensional example up to this point, that left to right, just on paper there, of our samples that are exactly 100 meters apart. So what about when you're in 3D? And this is where we're looking at my data set this is an invented data set. We have a really, really high grade trend along a vein, really spatially restricted, really hard boundaries, and just an insane density of drill holes for that kind of continuity. So this is really good for just visually striking examples, which is why I like using it, but it isn't a real data set. So in 3D, you want to know what your deposit is doing. What are my directions of maximum continuity? Where should I weight samples preferentially in some directions versus others? And that's where variogram modeling in 3D comes from. So each individual variogram is along a single direction, and it highlights what the range is for that direction. So at what range, at what distance are samples separated where they're no longer related to each other? And since deposits are spatially restricted, there's often greater continuity or longer range along certain directions versus others. So variograms generated in many directions, so multiple of those variogram charts can highlight areas of longer or shorter continuity. They'll have a bigger or smaller range depending on which direction they're looking at and which samples they're comparing. If you model all these together, you can create a 3D variogram model, which is what you need to do an interpolation, because for every block in the block model, you want to be able to look at any of the samples around it, and no matter what spacing they are, or no matter where they're sitting relative to the block model, you want to be able to know how to weight it properly. And that's what the end game of creating a 3D variogram model is an ellipsoid shape. Within that shape, you know exactly what the variogram value is anywhere in that space. So the samples in certain directions can be weighted for that weighted average properly. So let's use this image as an example. So imagine what the ranges are going to look like for a block that you're interpolating using a sample at the end of the blue arrow and a sample at the end of the green arrow. So the blue arrow is much closer to the block. So if we were just doing this as an inverse distance, it's going to get the majority of the weight, 80 or 90% of it. And the green sample is much further away. So if this was strictly inverse distance, it wouldn't care where the samples are sitting. It would just see how far away they are from the block and then do their weighting in that way. However, variograms can be able to show us that maybe the range in one direction is better than the range or longer than the range in another. Maybe there's greater continuity in one direction than there is in the other. And just from a practical standpoint, if you were to estimate this block and you were only to take the two samples indicated by the arrows, which one would you give more weight? Would you do the one along the trend of the deposit, along that vein, or the one across it just because it's closer? So which direction has a greater range and which direction has a shorter range? And this is what variograms can help you see. So if I was to generate a directional variogram along the blue direction and look at all the samples at different lag spacings, you can see that that variogram value increases very quickly and reaches that kind of level off point quite soon. So it's already crossing over the variance of the overall data set at only about 50 meters or so before leveling off and no longer becoming correlated, which to us spatially, visually makes sense. If you're comparing any samples in this direction, no matter where you're comparing them, at a certain distance, they're going to be different because you're going to have high values versus low values. Whereas if you create a variogram in the green direction, the range is much bigger. You can see you're looking at 450, 500 meters of separation before they start leveling off. You have a lot of similarity for much, much longer distances. So despite this being much further away, it should probably get at least equal, if not more weighting to the one that is closer. And keep in mind, I placed this block in the center of this kind of ore vein just to make it visually instructive. But these rules, the variogram model is for the entirety of the deposit. So if I was to put this block anywhere, the variogram model would tell us that samples, can you see my cursor on the screen share? I'm not sure. Okay, perfect. So if I was to look at a block here and look in this direction, on average, samples along this azimuth will always be more similar to each other because they're parallel to that high ore vein than samples in this direction, because at some distance, you're going to have samples that don't agree. And remember, when you're doing a variogram, you're sampling every single data point. So at some point, when you're sampling your tails and heads in this direction, you're going to have highs mixing with lows, which have a greater overall average difference. Whereas if you're sampling this direction, you're always going to have either just lows that are very similar or just highs that are very similar. So you'll never actually have a very big difference between them, and they'll have a greater range. So blue direction, variance or the average difference increases very quickly with distance separation. And then the green direction, the range is much larger, so samples separated by much further apart are still more similar. Ready. So you can create a bunch of these individual directional variograms and plot them all on top of each other and have an idea and try to suss out where the short or the long directions are. But there's something called variogram maps that kind of help you with that. This is a heat map of variance. So what it's doing in the background is just creating a whole bunch of directional variograms and then just sort of interpolating between them and giving you a heat map of variance. But it makes them much more visually instructive for us humans to see, rather than look at a bunch of 2D ones and try to discern by filtering between them and figuring out where the lowest are. So the variogram maps summarize this information in 3D heat maps. And they can also assist you in calculating, and again, these terms might be familiar if you worked variograms before, your major, minor, or vertical, or depending on what software you use or kind of what background you have in it, it can be your major, your semi-major, or your minor, because it wouldn't be geology if we had multiple confusing terms for things that mean the same thing. Same thing here. So in my software, in my terms, it's major, minor, and vertical for the main direction of continuity, the second greatest direction of continuity, and the third direction of continuity. And these are 3 perpendicular directions, which is important because if I know the range of my variograms in those 3 perpendicular directions, I can use them to create that ellipse, that variogram model that I was mentioning before, that we'll be visualizing in a couple of slides here. So variogram maps can be a little confusing to visualize and orient with your data, which is why in MindPlan we have this handy dandy heat map visualizer where you can place this variogram map, so this heat map of variance in 3 perpendicular directions against your data set and be able to do sort of a visual validation, which is one of the most important steps in any geomodeling or interpolation, is to actually check, does this visually make sense with the data that I'm seeing? And sure enough, I have that really cool cross section because it's laying directly on the direction of greatest continuity or right along the trends of that high grade vein. And you can even see it in the other cross sections there, kind of that high direction. And it's recommending that my major direction be along that green axis, my minor be along the red, and then my vertical be along the blue. So I can export those 3 directions, as directional variograms. And they'll look like this. So fitted to the vein on my major, fitted the vein on my minor, and fitted the vein on my vert. I said fitted the vein, that was just what I called it. It's not really fitting it to the vein. Again, this model is valid throughout your entire data set, like I was mentioning before. And then you fit those curves to the model. So these are perpendicular, and you can use as many variograms in a model fit as you want, but 3 perpendicular directions makes it more visually instructive. So the range of the major, the range of the minor, and the range of the vertical. This creates an ellipsoid defined by the ranges of variograms and by these variogram curves. And because we have that ellipse defined by a curve in each of the major directions of that ellipsoid shape, we now know anywhere within the ellipsoid space what the variogram value should be for any different distance, for any direction, for any block. And we have a visualizer for that too, because I'm a very visually instructive learner. And you can see what my variogram ellipse looks like and where the maximum ranges end up sitting. So you can notice if I change the range of the major, the ellipsoid shrinks because I'm telling it anything before this is no longer correlated. And same with the minor, it's shrinking it along the red direction now. And that helps you visualize that within this ellipse, I know what each of my variograms are on each of the major directions, the perpendicular directions. So that's what you need to define ellipses, those 3 perpendicular directions. I can define a range, and I can define a variogram model for each of them. And that means anywhere within that volume of space, I know what the variogram value should be. And that means I can estimate a block using samples anywhere around it and be able to get them weighted appropriately. Alrighty. So using what we've learned, let's try this estimate again, except this time we're going to Krieg it using a variogram model. Just a moment here. So remember this example with inverse distance, it just ended up being a straight average. They were spaced equally. Inverse distance only cares about spacing, it doesn't care about direction. So this just ended up both being weighted evenly. In this case, let's say we have a variogram model, just a simple 2-dimensional one. It's going to tell me that the range at 90 degrees rotation, so let's say that's left to right, so east-west. So if I was to look along east-west, the range is 500 meters. We have a greater range. So across a greater separation distance, my samples are more similar. And then at 0 degrees, so let's say this is north-south, it's only a range of 150. So the samples become more different more quickly at shorter distances than in my east-west direction. So samples are more related to each other at a greater distance left-right than they are up-down. So I'm not going to go through the Cretan calculations, but just as the summary, the weight that ends up getting assigned to this grade value, despite them being equally spaced, is much higher. It gets 75% of the weight versus just 25% of the weight for the other sample, because the variogram value is telling it this direction, samples are more continuous, they're more related to each other. So this should get more priority. Whereas on this side, maybe this is outside the vein, if we're looking at thinking of the example that I was looking at, or outside of the vein trend that you're seeing in your deposit, it's getting punished. Well, punished maybe not the right word, but it's being weighted less despite being equally distanced away. And we end up having a final estimate. When we did with inverse distance, it was a final estimate of 0.8. When we did it Krieged with a model that was more continuous in this direction, the higher value gets way more of the weight, so you get a much higher weighted average of 0.95. Okay. All right, so just quick summary: difference, distance, and direction. That's all a variogram is telling you. It's telling you in a certain direction along a certain azimuth, what is the average difference between samples separated by a certain distance, or your lag. And you can use that to determine in your interpolations how much should samples be weighted based off of their distribution around the area that you're estimating. Are they along a trend? Are they outside of the trend? Are samples that are along this direction more continuously related than in other directions? So interpolation, in essence, is just a weighted average of the surrounding samples that you're using to interpolate that block. And because deposits are spatially restricted, their difference depends on distance and direction. And the variograms model that average difference at certain distances and in certain directions for everyone in your deposit, and then can inform the interpolator how values should be weighted for that final sample. So samples along directions or trends of greater continuity will end up getting more weight, even if they're equally spaced versus another sample, or even if they're further away, depending on how your variogram model is informing on it. Yeah, and then finally, any of the images that you saw here, except for the ones that I otherwise referenced, the 3D images were all modeled within MinePlan 3D. That's a comprehensive geoscience and engineering software for doing geomodeling, engineering plans, grade control, all that great stuff. And I'll make my email available to reach out if you want to see any more of the geology, because this just covered a very small aspect of it. And yeah, I'll leave it open discussion now. That's all I have.
Thank you so much. I really appreciate you taking the time to talk to us. There's already been lots of thank yous and things coming through, so I think everyone really, really enjoyed that. So thank you.